Forces are given many names, such as push, pull, thrust, lift, weight, friction, and tension. Traditionally, forces have been grouped into several categories and given names relating to their source, how they are transmitted, or their effects. If the force supporting a load is perpendicular to the surface of contact between the load and its support, this force is defined to be a normal force and is given the symbol N. Please note that this N is different from the unit of force, Newton. The word normal means perpendicular to a surface. The normal force can be less than the object's weight if the object is on an incline. When an object rests on an incline that makes an angle theta with the horizontal, the force of gravity acting on the object is divided into two components: a force acting perpendicular to the plane, W perpendicular, and a force acting parallel to the plane, W parallel. Notice that the angle theta of the incline is the same as the angle formed between W and W perpendicular, so that W perpendicular equals to mg cosine theta and is typically equal in magnitude and opposite in direction to the normal force N. W parallel equals to mg sine theta and causes the object to accelerate down the incline. The force of friction, F, opposes the motion of the object, so it acts upward along the plane. A tension is a force along the length of a medium, especially a force carried by a flexible medium such as a rope or cable. Not coincidentally, the flexible cords that carry muscle forces to other parts of the body are called tendons. It is important to understand that tension is always a pull in a flexible connector, since you can never push a rope, and tension is always parallel to the connector's length. Consider a person holding a mass on a rope as shown in this picture. Tension in the rope must equal the weight of the supported mass. Since the mass is stationary, its acceleration is zero. According to Newton's second law, the net external force should be zero. From the free body diagram, we see the only external forces acting on the mass are its weight W and the tension T supplied by the rope. Thus, F net equals to T minus W equals to 0. That gives T equals W equals to mg. Flexible connectors are often used to transmit forces around corners, such as in a hospital traction system, a finger joint, or a bicycle brake cable. If there is no friction, the tension is transmitted undiminished. Only its direction changes, and it is always parallel to the flexible connector. Let's look at this example together. As you can see in the figure, the wire is not perfectly horizontal, but is bent under the person's weight. Thus, the tension on each side of the person has an upward component that can support his weight. The system of interest is the tightrope walker, and the only external forces acting on him are his weight W and the two tensions. It is reasonable to neglect the weight of the wire itself. The net external force is zero because the system is stationary. Since we have a two-dimensional vector problem here, the easiest method of solution is to pick a convenient coordinate system and project the vectors onto its axis. In this case, the best coordinate system is the horizontal and the vertical axis. We first resolve the tension vectors into their horizontal and vertical components, and draw a new free body diagram showing all of the horizontal and vertical components of each force acting on the system. Considering the horizontal components of the forces, we have F net x equals to 0, so that TL equals to TR. Considering the vertical components, we have F net y equals to 0, so that TLy plus TRy equals to W. Solving for the tension T, we get T equals to W over 2 sine 5 degrees, and the result is 3,500 Newton. We have talked about some basic problem-solving skills when we study one-dimensional kinematics. All of them apply here, but there are some specific strategies useful in applying Newton's laws of motion. As usual, it is first necessary to identify the physical principles involved. If it is determined that Newton's laws of motion are involved, that is, if the problem involves forces, it is particularly important to draw a careful sketch of the situation. For example, in this sketch, we can use arrows to represent all possible forces. The tension of the rope, T, the weight of the person, W, and the forces the person applies to the rope, Ft. We label the forces carefully and make their length and direction correspond to the forces they represent. The second step is to make a list of the known quantities and the quantities that need to be determined. It is very important to carefully determine the system of interest. This decision is a crucial step since Newton's second law involves only external forces. Once the system of interest has been identified, it becomes possible to determine which forces are external and which are internal. For example, in this sketch, if we define the system of interest to be the person, then the force Ft is no longer shown in the free body diagram because it is a force applied by the person on the rope, not a force acting on the person. A diagram showing the system of interest and all of the external forces is called a free body diagram. Only forces are shown on free body diagrams, not acceleration or velocity. Once a free body diagram is drawn, Newton's second law can be applied to solve the problem. If the problem is two-dimensional, then it must be broken down into two one-dimensional problems. Before you write net force equations, it is critical to determine whether the system is accelerating in a particular direction. If the acceleration is zero in a particular direction, then the net force is zero in that direction. Similarly, If the acceleration is non-zero in a particular direction, then the net force is described by the equation Fnet equals to ma. The last step is to check if the answer is reasonable. We will have more practices about these problem-solving strategies using some interesting examples in the group working questions. Physics is most interesting and most powerful when applied to general situations that involve more than a narrow set of physical principles. For example, Newton's laws of motion can be integrated with kinematics because forces produce accelerations, which affect the velocity and displacement. The problem-solving strategies of these integrated concept problems are: first, identify which physical principles are involved. It could be Newton's laws of motion, or kinematics, or both. Second, solve the problem using strategies related to the specific physical principles. We are using this example to illustrate how these strategies are applied to an integrated concept problem. In question A, we are given the initial and final velocities, and the quantity to be solved is the average acceleration. This is the kinematics question. By definition, the average acceleration equals to delta v over delta t, that is 3.20 meter per second squared. In question B, we are asked to find the average force the player exerts backward to achieve this forward acceleration. This is related to Newton's laws of motion. According to Newton's third law of motion, the average force the player exerts backward on the ground is equal in magnitude to the net external force on the player, which is the force that causes the player's acceleration. Since we already know the player's acceleration and his mass, we can use Newton's second law to find the force exerted, which is 224 Newton. You may or may not have heard about it, but in physics, there are some forces that are real, whereas others are not. Real forces are those that have some physical origin, such as the gravitational pull. On the other hand, fictitious forces are those that arise simply because an observer is in an accelerating frame of reference, such as the force you feel in a merry-go-round or when a car slows down. An inertial frame of reference is one in which all forces are real, and equivalently, one in which Newton's laws have the simple forms given in this chapter. The crucial factor in determining whether a frame of reference is inertial is whether it accelerates or rotates relative to a known inertial frame. Earth's rotation is slow enough that Earth is nearly an inertial frame. Ordinarily, one must perform precise experiments to observe fictitious forces and the slight departures from Newton's laws due to Earth rotation. However, on the large scale, such as for the rotation of weather system and ocean currents, these effects can be easily observed. We have talked about many different types of forces, and there are many more, but it is not necessary to discuss every type of them. One natural question to ask is, are there some forces more basic than others? Are some forces only different manifestations of the same underlying force? The answer to both questions is yes. One of the most remarkable simplifications in physics is that only 4 distinct forces account for all known phenomena. The 4 basic forces are the gravitational force, the electromagnetic force, the weak nuclear force, and the strong nuclear force. On a macroscopic scale, electromagnetism and gravity are the basis for all forces. Except for the gravitational force, all the other forces we experience directly in our everyday life belong to the electromagnetic force. You may read the chapter 4.8 for more information on this topic, and we will literally define these 4 basic forces in future chapters of this course and the following course, Physics 112.